Hey everyone, and welcome. I am absolutely thrilled you're here for this explainer today. If you're studying electrical or process engineering, well, you can go ahead and consider today's session your foundational masterclass. We are diving deep into one of the most critical, challenging, and honestly fascinating topics in the entire field, mastering chemical reactor temperature and level control. We'll be digging into some dynamic modeling data to see exactly how different mathematical controllers actually behave out there in the real world. So, let's get into it. Now, let's kick things off with a pretty high-stakes question. How do you actually tame a boiling chemical reactor without it overflowing, drying out, or just completely spiraling out of control? Out in the industrial world, this is a massive challenge. You've got this incredibly delicate balance to strike. On the one hand, you absolutely must prevent safety hazards and physical damage to the reactor itself. But on the other hand, you can't just blast it with endless cooling water or steam. That wastes a massive amount of energy and sends your operational costs right through the roof. What you need is a system that performs beautifully, but also operates with serious efficiency. Okay, here's our syllabus for today as we hunt for that perfect Goldilocks temperature controller. 1. The high-stakes reactor. 2. The power of feedback. 3. P control, the quick reaction. 4. PI control, fixing the error. 5. PID control, ultimate mastery. And finally, 6. The controller showdown. All right, let's jump right into section 1, the high-stakes reactor. So every control system out there can be broken down into a few specific variables. And really wrapping your head around these is your very first step as an engineer. First up, we've got our manipulated variables. These are the elements who can actively change. Think of opening a steam valve or maybe adjusting the fluid inflow. Next, we have our controlled variables. This is our ultimate target, right? Like maintaining a very specific reactor temperature or a certain liquid level. And finally, we have the villains of our story, disturbances. These are the chaotic, unpredictable outside forces constantly trying to mess up our perfect system. That could be a sudden fluid outflow or ambient heat just leaking out into the room. Moving on to section 2, the power of feedback. When you don't use feedback, the source data shows us exactly what happens. It's basically an open-loop disaster. If you apply a step input of steam without any kind of control mechanism, the system becomes incredibly sluggish and the temperature just uncontrollably increases. It blindly accepts the input without ever bothering to check the output. And if one of those disturbances hits, an open-loop system has absolutely zero ability to reject it. It is literally like driving a car blindfolded with a brick resting on the gas pedal. Total chaos. To fix this disaster, we built a closed loop, or what we call a feedback system. The logic here is beautifully simple, but it's highly effective. Step 1, we constantly measure the actual reactor temperature. Step 2, we compare that measurement to our desired target, our set point, to calculate the exact error. And step 3, we automatically adjust our manipulated variable, which is the steam valve, to shrink that error down. The crucial takeaway here is that a feedback loop is just a continuous, relentless fighter against those system disturbances. But exactly how we calculate that adjustment, well, that makes all the difference in the world. Which brings us to section 3, P control, the quick reaction. This equation is the absolute most basic reaction math we have. The output of the controller, which is U of t, is simply the current error, E of t, multiplied by a proportional constant, Kp. To put that in plain English, if the temperature is a little bit too low, open the steam valve a little bit. If the temperature is way too low, open the valve a lot. It's just a direct, immediate reaction to whatever is happening right at this very second. Now, when this is tested in the simulation, the proportional controller's behavior is super distinct. It gives us a really quick initial climb. It attacks that error aggressively, but it has a fatal flaw. It cannot completely remove the steady state error because it only acts when there is a present error. As the system gets closer and closer to the target, the pushing force just gets weaker and weaker. Ultimately, it stalls out, leaving you with this really annoying, persistent offset. You'll get close to your target temperature, sure, but you will never actually hit it perfectly. Section 4, PI control, fixing the error. Now, this equation right here is brilliantly elegant. We keep our proportional term, but then we add an integral term. That little integral symbol, think of it as the controller looking into the past. It mathematically accumulates all of the past errors over time. So even if that annoying offset from the P controller is tiny, the PI controller just keeps tracking it, adding it up minute by minute, until that accumulated history of error becomes large enough to force the steam valve open just a little bit more, closing the gap entirely. The reaction curve for this PI controller is just fantastic for accuracy. Okay, yes, it rises a bit more slowly than a pure P controller. It kind of takes its time.
but it completely eliminates that steady-state error. It hits the set point precisely, right on the money. The simulation data specifically notes that this makes it incredibly appropriate for slower systems, like reactor fluid level control, where what you really want is a smooth response that perfectly holds the level even when you have fluctuating outflow disturbances trying to mess it up.
All right, Section 5, PID Control, Ultimate Mastery.
Here is where we take our PI equation and add the final piece of the puzzle, the derivative term, KD. So if proportional looks at the present error and integral looks at the past error, derivative looks directly into the future. It calculates the rate of change of the error. If the temperature is rocketing toward the set point way too fast, the derivative term senses the steep slope and actually hits the brakes before the temperature overshoots the target. It's honestly exactly like having a mathematical crystal ball.
When the simulation applies PID control to the reactor temperature, the dynamic behavior is the smoothest and most precise yet. It offers incredibly fast, accurate predictive correction. You get absolutely zero offset and very, very little overshoot. But there is a major caveat to keep in mind. Because the derivative term is calculating the rate of change, it is highly sensitive to system noise. If your temperature sensor is jittery, the derivative term is going to overreact, thinking those tiny jitters are massive, sudden shifts. But if you tune it correctly, it's hands down the most complete controller for complex thermodynamics.
Let's wrap it up with Section 6, the controller showdown. Okay, this is your ultimate cheat sheet summarizing the core takeaways from the simulation data, directly comparing the efficiency of our three options. The P controller gives you a quick climb but leaves you stuck with an offset error. The PI controller fixes that steady-state error and finishes precisely, but it definitely sacrifices some speed to do it. And finally, the PID controller combines the best of all worlds. It's smooth, fast, accurate, and has no overshoot, but it strictly demands clean signals because of its sensitivity to noise. For you engineers out there, this matrix right here is your core decision-making foundation.
Now, what's truly amazing is how we actually apply all of this in the real world. You see, you don't have to choose just one. The source simulation concludes that the absolute most efficient way to manage reactor temperature is to use a cascade system. You basically use an outer PID controller to track the main reactor temperature because it's fast and predictive, but then you feed its output into an inner PI controller, which specifically manages the fast-acting steam jacket dynamics. Layering these controllers together gives you incredibly quick reactions to internal disruptions while maintaining absolutely perfect precision. It is pure engineering harmony. Which leaves us with this final thought for today. We've seen how the math of P, pi, and PID controllers can take a highly volatile, boiling chemical reactor and safely, efficiently bend it to our will. As electrical and process engineering students, these mathematical tools are now squarely in your hands. So if a PID loop can tame a chaotic reactor, what other complex engineering dynamics will you conquer with it in your career? Something to really think about. Thank you so much for joining me for this explainer. Keep designing, keep innovating, and I'll catch you in the next one.